Hey, let's finish the quiz review for 3.1 to 3.4. Number 6, we have our function x cubed minus 12x squared minus 27x. Use the first derivative test. Now we're going to be finding the relative extrema, but just the x values here. So we're going to go to the first derivative test, find the derivative function, set that equal to 0, factor out the 3, and then the remaining factors, we get 9 and negative 1. We put them on the sign line, and then we test each. We test values in each region with the derivative function. So plug negative 2 into the derivative function. We'll get a negative and a negative, which is a positive. Here I can plug in 0. I get negative and positive, which is negative. Here I can plug in 10. I'll get positive and positive, which is positive. So we see that there's going to be a relative maximum at negative 1 because they're changing sign from positive to negative, and then relative minimum at 9 because the graph is going from negative to positive. So relative maximum at x equals 1 because f prime changes from positive to negative. Rising slope to falling slope will create a relative max. And then relative minimum at x equals 9 because f prime changes signs from negative to positive. So a falling graph followed by a rising graph will indicate that there's going to be a relative minimum there. And if we wanted to find here, it's only asking for x values, but if it's asking you to find the ordered pairs, then you would plug these x values back into the original function. All right, so remember, the original function will produce physical location y values for you. The derivative function will produce information about its slope, whether positive meaning that the graph is rising, negative would mean that the graph is falling. Okay, number 7, we have our function. Find the intervals where our function is concave up and concave down, and find all points of inflection. So concavity requires us to get to the second derivative, so let's take those steps. X cubed plus x squared minus 21x. We go through our derivative rule, power rule. We get 3x squared. X squared becomes 2x. 21x becomes 21. We keep going because if we stop here and find critical values, then we'll be looking at potential where the slope is 0. But this is asking for a concavity, so we're going to keep going and find the derivative once again. So 3x squared becomes 6x. 2x becomes 2. 21 goes to 0. Now we can find critical points. Now we're down at the second derivative level. So set the second derivative function equal to 0. And we can solve for x. We get negative 1/3. There's only one critical value. We put that on a sign line. And then we test values in each interval. So here I can choose negative 1. Negative 1 into the second derivative. Remember, we're trying to determine concavity. So this is not going to go in the original function. It's not going to go in the f prime. This is going to go in the second derivative. We want to find out information about its concavity, about its rates of change of slope. So negative we choose negative 1 into the second derivative. We'll get negative 6 plus 2, which is a negative value. So we know that this portion of the graph will be concave down. If I plug in 0, I'll get a positive value. So we know that we have concave up here. So concave up will be from negative 1/3 to infinity because f double prime is positive. Concave down will be from negative infinity to negative 1/3 because f double prime is negative. And the point of inflection will be at 1/3 because there's a change in signs. So if we plug negative 1/3 back into the original function, we're going to get the physical y value, which is 7.074. because f double prime changes signs. All right, number 8. Use the second derivative test to find all relative extrema. So we're going to use the second derivative f double prime to determine whether we have a relative max or min rather than using the first derivative test. Okay, so here are the steps. We're going to find the derivative function. 6x squared minus 2x minus 20. We go through power rule to get that. We go through and we factor, and we're trying to find candidates now for relative max and min. Factor out the 2, and then the remaining terms will give us negative 5/3 and 2. So now, rather than putting this on a sign line, we're going to be plugging this into the second derivative function. But let's find the second derivative first. So 6x squared is first derivative, minus 2x minus 20. We're going to find the derivative once again. 6x squared becomes 12x, negative 2x becomes 2. So now we're going to plug each of these candidates into the second derivative function. So negative 5/3, we plug that in first, and we'll get negative 22. Now, negative 22 means that this graph, or this portion of the graph, will be where the graph is concave down. So if you have a slope that is 0 as well as part of a concave down graph, then you're going to be expecting a relative maximum. Okay, so because we have a slope of 0 and concave down, we know that this graph must have a relative maximum at negative 5/3. Okay. If I plug the other critical value, 2, into the second derivative, I'll get 24 minus 2, which is 22. 22 is greater than 0, so we know that this portion of the graph has a slope of 0, and it is part of a graph that is concave up. So we have a part of the graph that's a slope of 0, and then that point is also part of the concave up graph. So the combination of those two will allow us to narrow down the fact that there must be a relative minimum at x equals 2. Okay, number 9, sketch a labeled graph of a function with the following characteristics. So f of 0 equals f of 2 equals 0. So we want the order pairs to be 0, 0, and 2, 0. F prime is greater than 0 if x is less than 1. So we can convert this to a sign line here. We know that we'll get a positive slope to the left of 1. So positive slope to the left of 1. F prime of 1 does not exist, so this could either mean there's a sharp point on the graph or that there's a vertical asymptote, so we'll consider that later. Okay, F prime is less than 0 if x is greater than 1. So we have negative slope to the right of 1. Okay, so put down the sign line. And then f double prime is greater than 0 everywhere except for at 1. So we know the graph is always concave up except at 1. So I'll put a critical point at 1, concave up, concave up. So we want a graph to resemble this shape, but then we want to consider that there may be a vertical asymptote or there may be a sharp point there. So if we think of it as a sharp point, then we can say that the graph is rising with a shape of concave up, and it's going to hit a sharp point here, and that point where f prime does not exist. And then to the right of 1, we have the graph falling, but then also still maintaining that concave up shape. Or we could have it being a vertical asymptote there. So the graph is basically the same thing. Instead of putting a sharp point there, we'll have the graph go to positive infinity on both sides as x approaches 1 from the left and from the right.